So another approach that's used to reduce noise is to apply a digital filter. In the last chapter, you may remember that would have been chapter 3. You might remember that we had a problem where we had a signal with quite a bit of high frequency noise, and what we did was we averaged 3 successive samples. One way to express that is to express that as a moving average, where x of n is your original signal. So basically, you're constructing a new signal at point n that is the average of the signal at point n minus 1, and point n minus 2. And what happens intuitively we can see is that your y of n signal will come out smoother because you're averaging away very rapidly changing transitions. So here's an example of a signal that has a couple of spikes. And basically, here's an example of taking a 3-point moving average and taking a 10-point moving average. And you'll notice that the 10-point moving average smooths out quite a bit more. You still see on the 3-point moving average, you still see quite a few remnants of some of the peakiness of the original signal. The 10-point moving average has smoothed that out quite a bit. Now, it's also possible, rather than having evenly weighted components to this average, you can basically make a weighted average. So for example, maybe your n minus 2 point, you don't want to carry quite as much weight as your n minus 1 point, and you don't want that to carry quite as much weight as your n point. So you can accomplish that by weighting the values on that weighted average or moving average filter. So when we construct a filter with the desired bandwidth, we call that filter design. We want to design filters in the frequency domain because we usually have some kind of knowledge of what range of frequencies we're interested in our signal. And so we do that in the frequency domain, but they're actually implemented computationally in the time domain via convolution. And there are two basic filter types. Finite impulse or FIR filters are basically filters that depend on previous values of the signal, previous and present values. So it's a standard linear process. It's defined in the time domain by an impulse response, and the frequency response can be found by taking the FFT of the impulse response. An infinite impulse response filter has some additional memory-based components. It's defined in the time domain by a difference equation, and it requires some additional tools in order to implement it. And basically, the frequency response is characterized by taking the FFT of a numerator and a denominator. So here's a schematic of an FIR filter. You basically have your input x of n. It's going to be convolved with a filter b of n, and b of n and x of n are rarely the same. Are rarely the same length. So x and b are convolved, yielding y. In the infinite impulse response, we're adding the result of x of n convolved with b of n to a feedback parameter. So we take our output, we feed it back and convolve it with a different set of weights. We sum those two together and that's our new output. And so that would be our infinite impulse response filter implementation in a block diagram form. It contains a feedback element. If a filter uses only current and past data, it's called a causal filter. In other words, the input is causing the output. And so any real-time system that we have, so something that's processing currently incoming data, has to be causal because you don't have access to the future. So you don't know what your future output is in order to feed it back to create your current output. If the data are already stored in a computer file, it is possible to use future values because basically the future values were recorded and stored. So a non-causal filter can be used in a computational system. Here's an illustration of a signal. This is an eye movement signal, and it's been contaminated with 60 hertz noise. And so taken from an EEG, so this is probably a vertical eye movement based on the way it looks. So you've got some 60 hertz noise, and two filters are implemented, both with a 10-point moving average. One is causal and one is non-causal. And so you can see if you blow up this portion of the curve, you can see that the non-causal filter basically does not have any time delay. The causal filter introduces a time delay. And of course, in the discrete world, that basically is a phase shift. So this time delay can present problems, especially when you're trying to go back and forth from time domain to frequency domain. So here's a little bit of a visual example of a non-causal filter implementation. So basically, this filter takes a pass sample. This is a 3-point moving average filter. It takes a pass sample, a non-causal filter. It takes a past sample, a current sample, and a future sample. It averages those three together to give you this point. So basically, you're taking the next point, averaging that together to give you this point. So you basically can implement that in MATLAB using an impulse function of 1/3, 1/3, 1/3, and the convolve routine. And then in order to make that non-causal, you use the option same. So here's an example. Find the frequency characteristics of a 3-point moving average filter and a 10-point moving average filter, assuming sampling frequency of 250 Hertz. So basically, we're going to do this by constructing the two impulse responses or sets of weights, and then we're going to take the Fourier transform using the FFT, and then we're going to look at the data and see what that looks like, plotting the magnitude in phase. And then we're only going to take half the plot because, remember, only the first half of the Fourier transform plot is unique. So here are our moving average filters. Here's the 3-point moving average and the 10-point moving average, and you'll notice basically they're the same. They've been given weights 1/3, 1/3, 1/3, and then the 10-point has been 1/10. Here's where the FFT is taken of the 3-point filter, and then it's repeated for the 10-point filter. And so here are the results. You can see that if you look at the magnitude of the frequency response of the 10-point filter, it's shown here in this top curve. The 10-point filter is in the bottom curve. The 3-point filter is here in the top curve. Okay, the fact that the 10-point filter comes down to 0 dB at about 25 Hertz, this basically means that this 10-point filter is cutting the higher frequencies off more effectively. And then the 3-point filter, you notice that it basically comes out down to 0.7 dB about here. So that 0.7 dB point would be roughly 16 Hertz for the 10-point and 40 Hertz for the 16-point, for the 3-point. So what's happening here is your 10-point filter is giving you cutoff more quickly. Sometimes that's what you want, sometimes it's not. Also notice that it just rolls off faster, and the phase characteristics, which cannot be that easily seen in this plot, is probably better to look at the textbook plot for this. You can see that you get these kind of zigzag looking things. What that is in MATLAB, when you get to negative 180 degrees, it shifts you up to 0. So the phase doesn't really look like this zigzag plot. It's actually continuously declining. It's just since when we do 180 degree rotations, basically the way MATLAB resets itself is it resets back to 0. So in summary, we apply these filters of varying lengths and varying weights in order to obtain a frequency characteristic that we want. If you do something very simple like design a moving average filter of equal weights, then it's important to you to know what the frequency characteristics of that look like, because you need to know what the filter's doing in the frequency domain. What's your bandwidth? How's it impacting the signal when you actually convolve it in the time domain? How's it impacting the frequency spectrum? Now, an entire course could be spent talking about the Z-transform and the implementation of moving average filters and impulse response filters in the time domain. But at this point, let's suffice it to say that part of the challenge in designing a filter to give you, usually your specifications are done in the frequency domain. And so you know what you want the shape to look like. So if we go back to that plot of what this looks like, you probably actually don't want the shape to look like this. You would like the shape to look more rectangular. So in order to have that shape look rectangular in the frequency domain, what you have to know is, what do your time domain characteristics look like of that filter? And it's probably not 1/3, 1/3, 1/3, because 1/3, 1/3, 1/3 in the frequency spectrum gives you this. So a lot of time and energy are put into in this chapter explaining how to, given a desired design in the frequency domain, how do you then figure out what those weights are in the time domain.